We begin with the question, if you are surrounded by multiple attackers, what is the optimal strategy for defense? If two attackers are moving in to strike, who do you defend against first? There is no simple answer to this question, but we can approach this from a robotics perspective, through the development of a custom defensive intelligence module for a standard robotic arm. Our goal will be to equip a defender bot with a shield and defensive intelligence, so that it not only blocks incoming strikes, but adapts its defense strategy to prioritize threats and reflect attacks. Utilizing the real-time physics-based simulation environment library PyBullet, we begin by creating an attacker robot capable of executing strike trajectories along an interpolated path. We move on to the baseline defense intelligence, where the attacker sword is projected onto a detection plane to calculate the defense intercept point. Then, this point is used to obtain joint angle commands for the robot via inverse kinematics. This primitive control method is actually sufficient for one attacker, but falls flat in a scenario with two attackers, as the defense bot cannot currently decide what the optimal control action is. Now, a plane is no longer sufficient for adequate defense, and we need to set up a three-dimensional detection zone around the robot to handle attackers from all directions. The robot shows great reflexes towards incoming attacks at high speeds and can even track attackers in the detection zone for preemptive defense, but obviously it struggles to make a decision on who to defend against because it still has primitive decision-making abilities. To solve this issue, we propose a more complex intelligence called the Threat Scoring Framework, the backbone of GRDN 1.0. This module lets the defender bot calculate scores for each threat dynamically and prioritize defenses based on these scores. The framework consists of 4 attributes. Proximity, which is how close a threat is to the defender's critical hit zone, where a lower proximity would indicate a higher threat. Time to impact, which estimates how soon the sword tip will reach the hit zone based on its velocity and current position. A smaller TTI indicates a higher threat. Trajectory alignment, which quantifies how aligned the sword's velocity vector is with the direction toward the hit zone. A higher alignment indicates a higher threat. And velocity magnitude, which reflects how fast the sword tip is moving. Faster moving sword tips mean higher threat because they allow less time for the defender to react. This opens up a realm of fun possibilities for us to give our defender bot a variety of defense strategies by simply changing the consideration of these 4 different attributes in the defender bot's final movement decision. Let's take a look at some of these different control scenarios. This approach uses a rule-based scoring system with adjustable weights, but other viable approaches to finding the optimal defense strategy could be training the defender bot using reinforcement learning to learn an optimal control policy by interacting with the environment, model predictive control to compute optimal control actions by predicting the future trajectories of threats and optimizing the defender's response over a finite time horizon, or optimization via gradient descent with constraints for real-time trajectory optimization. By further integrating techniques like this, our system can transition from being a reactive defender to becoming a master strategist. Thank you for watching.